See my screen, all right? Okay, yeah. So thanks. First, I would like to thank Michael for inviting me here today. Um, and for this group meeting, I thought I'll share with you my work on the odd dynamics of living chiral crystal. And since I think most part of this what I'm going to present to you has been published, I think maybe it's more fruitful if you can ask questions. So please feel free to interrupt along the way for any questions that you might have. Um, Okay, so before I begin, I thought maybe I would first put this work in the larger context of what I'm interested in. So broadly speaking, what I'm interested in is trying to understand biological matter as a kind of active matter. And what I mean by that is that uh, these are systems where you get these constituent particles that consume energy, which break details balance at the microscopic level. And this typically will lead to spontaneous organization of emergent structures and novel material properties that you don't typically get in equilibrium materials. And so, in particular, in the past decades or so, a lot of work has been done to try to understand how we can describe and characterize some kind of biological system using polar and nematic order. And the most prominent example is probably how cells in tissues can actually behave like liquid crystals. And using this kind of framework, people are able to understand how spontaneous flows can arise in cells and tissues, especially in the context of morphogenesis. In the context of bacterial suspensions, people have shown that if you push the system hard enough in terms of how active they are, you can actually get into a regime of active turbulence with some interesting parallels with what people have known for many, many decades in fluid dynamics turbulence. And more recently, there's a lot of interest in trying to understand how topological defects in these polar nematic fields in tissues, for example, in this work from Kinneret-Karen's group, Hydra, they show that actually defects in this polar nematic field actually correspond to biologically significant organization centers. Um, and so this is really a very active area of research. But for today, I wanted to sort of focus on another kind of order that can arise in biology, and that is chirality. And of course, as we know, chirality is a very common features that we see around us. So the most prominent example is probably our left hand and right hand. Those are chiral because you cannot superimpose them by just purely rotation or translation. You have to have a mirror before you can superimpose them on themselves. And this gives it a very interesting physical properties that when you get collective behavior in self-organization of many of such particles, you get a new type of material properties. And so this chirality in synthetic or biological active matter has recently attracted a lot of attention. So, and one example here that I'm going to show you is the work from William Irvine's group at Chicago. And what they have here is that they have a spinning colloidal magnets. So basically they have these tiny colloidal magnets that they assemble thousands and thousands of them, and then they apply a magnetic field across it. And because of the setup, this colloidal particle actually all started spinning in the same direction. And what they found was that they can, using this setup, they can assemble this chiral fluid whereby you get a lot of very non-trivial non-equilibrium physical properties, including topological edge effects, as well as odd viscosity. So which I will go into more details in a moment. And this type of behavior really comes from the fact of each of these individual particle breaks chirality at the particle level. And this type of property has also been recently reported in a biological system. So a group in Japan, Yamauchi et al., they showed that if you culture some this neuroprogenitor cells in micropattern devices, they start showing this rotation behavior. And at the boundary, you get chiral H flows, which are signatures of chiral fluid. So by now, there has been quite a few examples of how systems can behave as chiral fluid. And in our project, we wanted to address this question in the context of a solid and ask whether we can find an odd response in biological active solid material. So to do that, we are going to use our favorite model organism, which is the starfish embryo. So here is a picture of a starfish embryo at about 48 hours post-fertilization. So they are about 200 micron in diameter. So can people see my cursor? Okay.
Yes.
Yeah. Okay, so they are about 200 micron in diameter and 300 micron in length. And on their surface, they are covered with this carpet of cilia, as with many marine invertebrates larvae. And of course, the cilia will beat and they start generating these hydrodynamic flows, which will allow them to swim in water. And what we found by accident, actually, was that if you culture enough of this embryo in, let's say, a six-well plate, what happens is that sometimes some of these embryos will swim towards the water-air interface. And because of the hydrodynamic interactions with the water-air interface, they will actually form a stable bound states so that they will remain perpendicular to the air-water interface stably. And then again, because of the hydrodynamic interactions, they will start attracting more and more embryos to itself. And because of this basic interactions, what you get is that you get this spontaneous self-organizations of starfish, thousands and thousands of starfish embryos. They will swim towards the surface, they will start attracting one another, and then they will self-assemble into these very regular crystalline structures. So I'm just going to let the video play one or twice and point out a few things about this. So one thing is that we're talking about millimeter size crystal, so you can actually see this by eye. The time scale is of the order tens of hours. So this crystal actually, from the time it starts assemble to its complete disassembly took about 30 plus hours. And as you can see, this crystal actually has very clear six-fold symmetry. It has this very beautiful hexagonal symmetry. It has all the features of what you would expect from a 2D isotropic crystals, where you get five-fold and seven-fold defects. You can get line of disclinations and etc. And of course, the most fascinating aspect about this system is that each of this embryo actually rotate in a chiral manner. Meaning to say, if you look from the top of this video, all of them are actually rotating in a clockwise direction. So that's where the chiral symmetry breaking comes in, that all of these particles rotate in the same way, they are chiral. And because of that, we expect the crystal to actually show elasticity that is distinct from what you would expect from just a plain old isotropic 2D crystal. So there's a lot that you can ask and do with the system, but initially we thought we just wanted to focus on three questions. The first one is how does this crystal self-assemble? What are the kind of emergent dynamics that you get from this chirally interacting particle, and what is driving this dissolution process of the crystal? So to address this questions of self-assembly, the first thing we thought was that it must come from hydrodynamics, because the embryos are firmly embedded in this water. So to measure the flow field around the embryo, what we do is this very standard PIV experiments. We just put beads around the embryos. I hope the video is clear enough that you can see that these beads are clearly moving towards the embryo, and because the water is incompressible, this flow field essentially the water get expelled down towards the bulk, like this blue arrow that we are showing right here. But near the top of the air-water interface, you get a net inflow of particles. And if we make this measure quantitative, what we found is that this is can be easily described by what is called a Stokes-Sillett flow. Essentially, it's the flow that is generated by a point force in a fluid. And you can see that we get very nice agreement between theory experiments. And of course, when we talk about self-assembly, we are talking about interactions between pairs of embryos, and this is where things starts to become interesting. So if you put just two embryos in the water and just look at how they interact, the first thing you notice is that, of course, each of these embryos again are spinning clockwise from our point of view. There's a net inflow of water of fluid flow. But on top of that, because of the rotation, they also started to show this orbital motion. Like, it's almost like two planets spinning around one another. And to first order, there are actually two types of interactions that is going on. One is that there's a transverse force interaction, which allows each of this embryo to start rolling on one another, essentially. The other kind of effect is actually, you can think of it as a kind of a friction effect, because these two embryos are spinning in the same direction. At the point of contact, they are actually moving in the opposite direction. So this embryo, at this point, they are spinning this way, but at this point, they're spinning that way. And because of that, they start to slow down one another through a non-reciprocal torque exchange. And from that, we are able to essentially, experimentally measure this flow field and show that it fits well into this description where you can, with a point force and a point torque, you can explain the flow field that we observe experimentally. So through that, we come up with a very minimal model for this chiral crystal formation. So essentially, we assume that each of this starfish embryo is a 2D disk. And in this 2D disk, the equation of motion essentially involves only three types of forces. One is that you get this Stokes-Lert attraction that is coming from the hydrodynamic interaction. You get a short-range repulsion because the embryos, once they get close enough, they cannot get closer anymore. And then you get this force from chiral interaction, which is essentially this transverse force interaction that I was telling you about earlier. And this transverse force interaction, or this orbital motion around one another, will depend on their rotation frequency omega here. To close this model, we have the equation for the individual rotation speed of the embryo, and this equation essentially says that the embryo likes to rotate in some fixed free rotation speed, but then you need to subtract away a net reduction in the torque that is dependent again on the embryo and its neighbor. So with this minimal model, what my theory collaborator, Alex, has been able to do was that he's able to recapitulate qualitatively the feature that we see in experiments. You start getting this small clusters that fuse together to form this big chiral crystals. And on top of that, we are able to quantitatively match what we measure in experiments in terms of embryo spinning frequency, as well as the large cluster rotation frequency as a function of a number of embryos. So that's all. That's sort of where we are in terms of trying to understand how this self-assembly process happens. And the next thing we wanted to understand is whether we get any emergent dynamics from the chiral interaction. So here I'll have to bring you through a little bit of coarse-grained continuum elasticity theory. So usually, typical when we talk about an elastic material and we talk about an elasticity of material, we usually have two modulus to describe that. They are so-called the shear modulus and the compression modulus, meaning to say, if I have a piece of material, if I squeeze it, how hard do I need to squeeze to produce some strain? That is compression modulus. The other modulus is the shear modulus. It characterizes how hard I need to shear the material before it actually goes out of shape. And that typically, so here the compression modulus and the shear modulus, at the microscopic level, this is because of the longitudinal force between the atoms. So you have atoms that attract and repel each other. How strong that interaction is roughly proportional. Well, in linear elasticity theory, is roughly proportional to your compression modulus and your shear modulus. But in our material, it is more interesting because we have, on top of this longitudinal interaction, we have transverse interaction. And that should, in theory, give rise to two more additional elasticity moduli. And this has been worked out in theory by Scheibner and al. In this paper right here. And what it means is that this type of transverse interaction should give rise to an odd compression modulus and an odd shear modulus. So the odd compression modulus essentially describes this property whereby if I squeeze the material from the boundary, this material will actually show a net torque in the middle, which is something that is very non-intuitive because it doesn't happen usually in our typical material. And an odd shear modulus is essentially describe this material property whereby if I shear this material, let's say in the vertical direction, the response of the material is that it gets sheared in 45 degrees. Again, the response of the material is rotated somehow by these chiral interactions in the particle level. So if you put this all, what I described to you in this matrix form, what it means is that in a typical isotropic passive solid, we get two modulus, which is the bulk modulus and the shear modulus right here. But if you have a chiral material, you get two additional modulus, which is A and K naught, that appears at the off-diagonal terms. And this kind of material properties you can only get if you have energy injection into the system, meaning to say your solid is out of equilibrium, because once you have this kind of moduli in the off diagonal, it means that you can extract energy from the system. And one thing that is predicted in this study right here is that if you have this type of material, you should be able to get strain cycles from the material. And this is exactly what we are able to observe in our experiments. So what we found is that through many iterations of the experiments, sometimes we see these spontaneous vibrational modes in our living chiral crystal. So I hope this video plays, but let me just show you. So essentially at about 3 hours time point, you can see even by eye, is that there's this very pronounced jiggling behavior in the crystal. So right about now, you should be able to see this vibration that propagates through the crystal. And to sort of first quantify that, what we did was that we do a particle tracking of each of this embryo. So each of this circle right here represents a single embryo. We are able to track their displacement. So that is what this little black arrow is showing. And the color code of this circles is essentially the angle at which the instantaneous displacement vector is showing with respect to the x-axis. And so so once we have done that analysis, what we found is that you can very clearly see that the displacement of each of these embryos show this very cyclic behavior, meaning to say you get this chiral active wave that is propagating through the crystal. And if you look at the phase, there's the propagation also shows some cyclic behavior. If we look at a single embryo and just track at this displacement, you can see that the periodicity of this displacement is of the order 240 seconds. So remember that these are embryos that is embedded in a fluid. So meaning to say it is the embryos are definitely in an overdam regime. So meaning to say this kind of excitation cannot be thermal in nature and must come from their non-equilibrium dynamics. And as I've mentioned previously, once you have a material that has a modulus, in principle, you should be able to get strain cycles from the material that is where we can extract energy from it. And indeed, if we did the analysis for this curl and divergence, as well as shear 1 and shear 2, we see this clockwise counterclockwise cycle in the strain space, which is very reminiscent of what the theory predict. And so now that we have seen signatures of odd elasticity in our material, the next thing that we want to ask is whether we can actually infer what the value of this odd, can we measure the odd elastic moduli? So usually when we want to measure elastic modulus from materials, we apply a stress, we measure the strain, and then we find out how they are correlated. In our system, because it's rotating and it's in this 6-well, 24-well plate structure, it's a little bit hard to perform the experiments. So instead, we try to infer this modulus from the defect strain field. So the math is a bit long and technical, but I just want to explain to you the idea behind it. And basically, the idea is as follows. If you have a solid and the solid has a topological defect, this defect will induce a displacement, a strain field around the defect. And depending on how the strain field looks like, we can actually infer whether there is whether the material is just an isotropic solid or whether there's a chiral component to it. And the theory behind it has been worked out in this PRL paper that was published in 2021. To cut a very long story short, what we are able to do here is that we are able to find the relative A and K naught modulus from this by going through this fitting procedure, and we found that both of the numbers are positive. And this is consistent with what we would get if we took our model from the hydrodynamic modeling earlier and cross-graded from the spring constants. And the fact that, and we found that they are actually, well, the values differ by quite a bit, but then at least the signs are correct. And what it means is that given that the cycles that we see are counterclockwise, it means that the material is actually doing work on the environment, which is consistent with what we would expect. So in this second part of the talk, what we found was that we are able to see signatures of odd elasticity in our material, and this is consistent with what you would expect if you have chiral interactions between the embryo. So in the last part of our work, we wanted to address this question of the spontaneous dissolution of our crystal. So if you look at this crystal information, you see that towards the dissolution process, the embryos are actually fluctuating more and more, and there's actually more disorder in the system. One way that we can quantify this disorder is that we can calculate this so-called local bond orientational order parameter. This is the mathematical definition of it, but then the intuitive explanation is that this psi6 parameter has two components. There is the real part of it, the magnitude, and the phase. So the magnitude of psi6 actually tells you how hexagonal-like locally an atom is. So if you are a perfect hexagon, then everything would be colored white. But then as you deviate more and more from this hexagon picture, you become more and more black in this color code. And then the phase of psi6 indicates the orientation of this hexagonal order. So essentially, the color tells you what the angle, what is the relative angle of this local hexagonal order with respect to the x-axis. So what we found was that if you just look at this magnitude of the psi6, which quantifies local hexagonal order, initially the crystals are relatively white, meaning to say they have very high hexagonal order. But then towards the end, you see that they get more and more of these hot spots before the crystals dissolves away, meaning to say disorders develops as the crystal dissolve. And if you look at this phase of the psi6, which is which gives you the orientation, initially you see that the crystals is largely just blue, or meaning to say all the the crystal is a single piece of crystal. They have the axis, the crystal axis is along some direction, but then as the crystal dissolves, you see more and more these patches of color, meaning to say the crystal is breaking into small and small pieces. There's more grain boundaries, and this is because you get more disorder in the system. We can be more quantitative with that by plotting this code called a probability time kymograph. So this kymograph, the vertical axis is the magnitude of psi 6. So remember, 1 indicates that the crystal is highly ordered. 0 means that the crystal is completely disordered. The x-axis is a time axis. So the crystal goes from 0 hours to 36 plus hours. And each of these vertical slices gives you the probability distribution of this magnitude of psi 6. So initially, when the crystals is highly ordered, you see that the distribution is highly peaked near 1, meaning to say the crystal is highly ordered. But then as time goes by, you see this more and more disorder develops towards the end, whereby you get a very long flat tail. So usually, again, if we compare this to an equilibrium system, what you get is that you get this kind of disorder to develop if you crank up some physical parameter. For example, if you increase the temperature as the ice is dissolving, you get more and more disorder in your crystalline structure. But what is remarkable in our system is that we are not changing any physical law. We're not changing temperature, not viscosity. What we are doing is that we are just letting the system run. So I'll explain this plot in a moment. And so what really is happening here is that, of course, we have a living system. So over the course of 30 hours, these embryos are not just sitting there. At the individual level, they are also developing and changing both their morphology as well as their flow field. And this actually introduced additional noise, effectively introduced additional noise into the system, which is driving this order-disorder transition. So essentially what we have is that we have symmetry breaking at a particle level that leads to this order-disorder transition at the crystalline level. And we can quantify this a bit further through two metrics. One is that we can quantify the shape anisotropy. So these are 3 snapshots of the crystal, again, when looking from the top. And what you will see is that initially, at about 10 hours time point, the embryos look roughly circular if you view from the top. But then they become increasingly elliptical because the embryo is developing and they're breaking more and more symmetry at a single embryo level. And in addition to that, because of this shape asymmetry at the embryo level, the embryo at the boundary becomes actually less and less stable. So for example, if you look at this 10-hour time point, you can see that this embryos at the boundary actually are really standing almost vertically. But then towards the end, near the 33 hours, a lot of the embryos are actually toppling sideways. So you are able to see the side view of these embryos, and then they started swimming away, and that's what's leading the crystal to dissolve. So basically what we have here is that essentially this dissolution process is really driven by the development of this embryo and not by any physical parameter. So that's basically what we have shown in our paper. But then, of course, as you can see, it's a very rich system, and actually there are many things that we can do with it, including many open questions. One of which is that I show you that there's this vibrational wave that propagates through the crystal. But then the question is, why is it that we see it sometimes, but then why do we not see it at other times? And so one thing that we did notice was that this wave dynamics seems to have something to do with the topological defects in our crystal. So if you look at this video on the right here, the defects in a 6-fold crystals basically, so usually in a 2D isotropic crystal, each atom will have a 6 neighbor arranged hexagonally. But when you get defects, it means that instead of 6 neighbors, you get either 5 or 7 neighbors. I mean, you can get 8 or 9, but then those are very atypical. What we found was that if we count the number of such defects, we see that, and then we plot it as a function of time, so that is a blue curve, and then we can quantify the degree of vibration that we see as the magnitude of this cycling. And that is the yellow plot that I'm showing right here. And what you see is that there's this interesting correlation between this uptick, a small uptick in the cycling magnitude, with this uptick in the number of defects, as well as when we get this very pronounced cycling behavior. That's because that corresponds slightly afterwards, after when we have this establishment of defects in the crystal, suggesting that there's some this defect somehow is providing the kicking that is needed to allow the wave to propagate, and that's something that we are actively investigating. Another question that we get a lot when we present this work is whether does this self-assembly behavior have any biological relevance. So, I mean, the short answer to that is that we don't know. Because if we want to investigate any biological function, then it will mean that we have to go out to the open ocean during when the embryos are developing and try to look for this millimeter-sized crystal in an open ocean, which is, well, not very feasible. But we took another route and asked, if the starfish embryo does this, does other species of marine invertebrate did it as well? So we check. So this is the species of starfish we work with, Pteria minata. This is a West Coast species. Asteria forbesi is an East Coast species. This is, I think, the purple sea urchin, of course, is an echinoderm species, which is a close relative of the starfish. And then we also look at this Platinares, which is a sea annelid. So it's actually, in the worm family, but then it's also marine like. So it's an outgroup in our comparisons. And in all the species that we have checked, they all have this ability at some point during their early development, whereby they can go to the air-water interface and spontaneously form this crystalline behavior. So then it begs the question of, if, through this different so I guess what we can say based on this data is that all this, it appears that many marine invertebrate species can do it, and whether this is purely an epiphenomena from their hydrodynamics or whether they really do serve some function, it's something to think about. But from a physics perspective, it does opens up another door of opportunity, because now we have this different type of atoms that we can play with and build different kind of living chiral crystals and see how the different shape and hydrodynamic properties can lead to different kind of material properties. And one thing that I'm interested in doing in my new lab at UCSD is that we are going to use Platinares to build a chiral crystal. And the exciting part about Platinares is that they are actually phototactic. So this is a sort of a schematic of this Platinares embryo through the first 24 to 30 hours. Unlike starfish, they have, instead of a couplet of cilia, they actually have a ciliary band near their equator. And beginning at about 24 hours, they start developing these eye spots at the tip, at the anterior side of their embryo. And this light spot actually allows phototactic behavior. So the hope is that we can somehow use light to actually manipulate rotation rate of this, the swimming behavior of this individual embryos, and maybe create patterns on this crystal. And first thing that we check is whether they form this crystalline structure. And what we found is that they do. Although, as this video, you can clearly see in this video, the crystal is not as stable as what we see in starfish species, but we suspect that we can probably tune this by changing maybe the viscosity or the buoyancy of the embryo. And when we measured the flow field around each of this embryo, you can see that to first order, oh, this is very preliminary data, but then to first order, you can see that they do show this dipole-like flow field that is very similar to starfish.
So can I ask a quick question?
Yes.
This is really cool.
Thank you.
Do you see a difference between the way they move between like the 13-hour and 24-hour, like the formations, like when the eye spot appears or before the eye
Oh,
spot?
so this is really very early work. The window, we're still trying to pin down where is the window where they form a crystal most robustly. But one thing that we can say is that it's not as robust as the starfish. So the starfish, you can I show you this 30-hour crystal, but at any point if you disrupt the crystal, they will reform again very easily. But then in the case of the platinum-rays, it seems like they are more sensitive. There's only one window, a tinier window where you can form this crystal. In this particular video, is about 24 hours. So it is at about the time point in which the eye spot has formed. But I suspect the ability to form crystal has more to do with the hydrodynamics rather than the eye spot. But it is also true that, if they are phototactic, then it means that we have to be a lot more careful about the light that we have in the lab, because that would affect their behavior, in turns would affect their crystalline. So it's something that we are working on.
Oh, thank you.
Yeah. So that's I think one very interesting, exciting direction that we can take by going to this toolbox that evolution has given us and look at different kind of marine species. But then, of course, we are also interested in a lot of the physics question, and one of which is the most base staple of statistical mechanics, which is that if you have a material, they typically go through phase transitions. In equilibrium type system, if you tune the temperature, you can get a material to go from solid to liquid to gas. In our embryo system, the starfish embryo system, we think that the dissolution process that we're seeing is actually more a sublimation process than a fluidization process. And the reason why I say this is because it is true that the crystal is getting more disorganized in the bulk, but then the reason why the crystal is dissolving is because the embryos are leaving from the boundary. So it's almost like it's evaporating from the boundary before our material completely fluidized. So one thing that we're hoping to do is that we are able to keep the embryo still at the air-water interface, but then completely fluidized, meaning to say they still maintain themselves at the air-water interface, but able to exchange neighbor completely and freely flow around. And what happens is that then you can ask what happens when this phase transition happens. And in 2D crystal melting theory, there's this idea that there's this people have shown that you are able to get this hexatic phase. And what I mean by that is that you get into this phase where you break translational order, but then you still have a long range orientational order. And we wanted to ask whether that still happens in a system where you have individual atom that is rotating in a chiral fashion. And of course, as with all physicists, what we are interested is in the phase diagram, except that now we have a non-equilibrium phase diagram where our axis is something like developmental time or buoyancy and viscosity, and ask whether we can get solid, liquid, or gas in our chiral crystal, and what happens at the boundary. The other interesting thing that we can do is to look at the cluster dynamics. So far, if you notice, the experiments that I have shown you show you a single crystal in the center of the camera. And that is because we are using a small well where you get this steep surface curvature, which creates a potential and push all the embryo to the center of the well, and you get only a single crystal at the end. But if you use a bigger well, so it basically means that instead of doing an experiment in a 24 well plate, you do it in a 6 well plate, you get a much flatter surface curvature, and what you get is something in this video right here. So you still do you get nucleation of multiple clusters, but then because you no longer have this steep potential, these clusters can remain by themselves. They don't all nucleate into a single crystal. But then you see that there's a lot more cluster dynamics that are available. So let the video loop once more. You see that now you have this multiple clusters, some of them rotate, some of them translate. Some of them has this very interesting, very oblong type of structure rather than clustering into a more isotropic structure. They merge, they separate. And then towards the end of the video, you will see this very pronounced jiggling behavior again. So right now, and that jiggling behavior is exactly the wave propagation that I was referring to. So I think, by simply changing the geometry of our experimental system, we can ask many more interesting questions like, why is it that some cluster rotate, some translate, and some both rotate and translate? What happens during this merger and separation events? And one thing that you might have noticed is that there's this very dynamic reorganization process. And indeed, if you take a pipette tip and try to disturb the crystal, they quickly fold back onto themselves and have this sort of a self-healing properties. And this is the one way that you can, yeah, go ahead.
Yeah, just a quick question. So if these things are living in the ocean, then there's going to be waves. So have you tried putting it in basically a wave pool?
Okay. So that's a good point. So what we found was that these are not very stable. Meaning to say, if you take the six, if you just jiggle the well, this crystals break apart quite easily.
Okay.
Yeah. Right. As I was saying, this idea of self-healing properties, it's interesting because if you just think about it, if you have a bunch of particles that are just attracting and repelling from one another, then if you break it, then the only way it can come back is to start attracting one another. But then right now, what we have is that a set of particles that can attract one another, and on top of that, they can roll on one another. And that gives it an additional ability whereby if you form a long crystals, is able to fold back onto itself. So there's an additional degree of freedom that allows these crystals to add one more dimension to their dynamics. And this is sort of where this idea of cluster dynamic and reorganization is going. And maybe one last thing that I want to mention is that, of course, so far, all that I've shown you is at the macroscopic crystalline level. There are also interesting questions to ask at what happens at a single embryo level. So I've shown you earlier that on the surface of this embryo, you have this ciliary structure. And in this video, I mean, people have spent many decades trying to study motor cilia and biophysics of cilia. But I think perhaps maybe not as much is known about how the cilia arrange themselves in a collective context. And one question is that I told you that the secret ingredient in our system is that each of this embryo is rotating in a chiral fashion. So how is it that the beating of this individual cilia coordinate with one another to make sure that all the embryos rotate in the same handedness is an open question. And of course, if you imagine that a cilia is just beating in a single plane, and we want to generate a rotating machine from a cilia that beats in a single plane, then one way that you would do it is that you can arrange it at a certain angle with respect to the axis of rotation, and that would give you a rotation. But that still doesn't answer the question of why is it that, how do they know that they need to slant leftwards or rightwards to give you this chiral. So I mean, this goes back to this big question in developmental biology of a left-right symmetry breaking in different type of organism. And the other more physics inspired question is that if you have this cilia being arranged on a closed surface like a sphere, it's known that you must have topological defects. So does the placement of topological defects actually affect how chirality is arise? And in fact, this is exactly what we have shown in a completely different study. So now I have to switch gear a little bit. And what I'm showing you is not an embryo, it's an organoid. So this is a pancreas organoid single epithelial layer. I just want to give you a very let me just give you a punchline of the study. What we found in this study is that if you get this form this a single epithelial like pancreas organoid, they do show a spontaneous rotation, but then these are cells that crawls on extracellular matrix, so there's no cilia involved. It's really just cell motility on an extracellular matrix. And we found that they do a spontaneous rotation. On top of that, if you look at the cell shape and measure the cell elongation axis, this cell elongation actually appears to make a preferred angle with respect to the axis of rotation. They show either a 45 degrees slant or a 135 degrees slant. And if you squint your eye and look at this cell orientation configuration, is essentially a mirror image of one another. Meaning to say, spontaneously rotating organoids actually show a chiral symmetry breaking. And to cut a long story short, what we are able to show is that using theory with experimental evidence, we found that it's really the topological defects of the cell polarity that breaks this chiral symmetry. Again, on a sphere, you always get topological defects in the orientation. And depending on whether you get an aster or a star-like defects or a spiral-like defects at the north and the south pole, you get either one of the chiral symmetry. So if you're interested, I'm happy to chat more offline. And this work is actually on bioRxiv now. But coming back to this question of chirality in our starfish embryo, I think there's a lot of interesting questions that you can ask in terms of cilia patterning, how it couples to development, and how that leads to chiral rotation. And just a side note is that one thing that I've been asking around to see if people have tried to keep track of whether embryos rotate clockwise and anti-clockwise, and it seems that most of them, in fact, I haven't found an example in which they rotate in a different direction. So that suggests some, evolutionary constraint or reason that gives all these marine invertebrate embryos the same handedness of rotation, which I suspect has to do with the cilia, which we know is definitely chiral. So with that, the last bit of self advertisement. So I just started my lab UCSD physics department. And the lab will focus on two things. One is this continuing on this road of chiral active matter that I talk about today. And the other part of the lab will be interested in organoid morphogenesis, where we use organoid to study collective cell behavior, morphogenesis, and tissue mechanics. So if you guys have and of course the lab is actively recruiting. So if you know of your friends who might be interested in some of this work, I would appreciate it very much if you could spread the word. And with that, I would like to thank all my collaborators for this work, especially Alexander Mitker, who now has a lab, who's starting his own group at University of Oxford, and he's responsible for all the theory in the talk. And yeah, that's all. I thank you for attention, and I'm happy to take any more questions.
Excellent. Thanks so much. That was really interesting. Anybody else have questions? I have a couple of things, but anybody else?
Yeah, I had a question. Cool talk. So on the last part where you were basically looking at the overall chirality patterns on a sphere and breaking off asymmetry on the sphere. Could you hypothesize what would constitute, like how would you have to break the symmetry and any kind of mechanism? So you get something like a flow pattern, like imagine like the Earth's magnetic field, right, where like flow lines go from the North Pole to the South Pole all around the sphere. Could you get something like that based on your model?
Yeah. So one thing is that so that is there's sort of two parts to your question. One is that whether the cells starts to flow, and in our case we are actually more of in a solid regime, meaning to say the cells do not exchange neighbor. So if you talk about cell flow, then the cells has to exchange neighbor.
No, sorry, I meant like the polarity of the cilia. So like I'm thinking about like cilia inducing movement of like flow of liquid around it. So the flow, I mean like the flow induced by the cilia around the sphere.
Okay. So in this context of the organoid, there's no cilia. The cilia, I should explain this a bit more. What we are seeing here is an organoid that grows in an extracellular matrix, the matrigel. And so the matrigel is the tissue has an apical basal polarity. Of course, the basal side faces outwards and crawls onto the extracellular matrix. The apical side faces inwards, and inside is just a fluid filled lumen. And these cells do have cilia, but the cilia is facing inwards, and the cilia is not motile. So the motility that we see here is purely from the basal side. So focal adhesion, like cell crawling on the extracellular matrix.
Okay. And just in terms of the cell polarity itself, same question just for the polarity, like having the polarity arranged in kind of like these longitudinal lines.
Yeah, so for the cell polarity, we suspect that there's probably no this hydrodynamic like interaction. Although you could hypothesize that maybe there's of course they are crawling on an elastic material, and this elasticity could transmit long range information for cell polarity alignment. But at least in our model, we kept things simple and say that this polarity only align with their neighbors. And of course, I suspect if you add this long range component to it, I'll have to think about whether there's any qualitatively different kind of mechanism that will allow chiral symmetry.
Cool, thank you.
Can I ask a quick question? So it seems like the sort of forming of the crystal and the breakdown of the crystal are dependent on the merger properties of the spin dynamics of the starfish embryos. And so I'm wondering if you had a mixture with heterochromic starfish, right? So I have some of the older ones when they're starting to break down mixed with the younger ones. What will happen there? Or what if I have most of the embryos are kind of normal, but then one or two of them are forming abnormally. They're sort of malformed, so they're going to rotate incorrectly. Would you expect those to kind of break the crystal or get extruded? Or
right? So for your first question, what happens when you mix this old embryos with young embryos? Some of my previous lab mates, they are trying exactly these experiments. The answer is that you get sort of a mix of behavior. In the sense that the old embryos is less stable, the young embryos are more stable, so they affect their own stability. It looks like they like to phase separate, meaning to say the old ones like to go with the old ones, and the young ones want to stick to the young ones. But there is no. I mean, so far it's not clear yet. It becomes a bit more uncontrolled, and it's not clear how they affect the properties, except to say that they are roughly an average of what you would expect from a purely old and purely young crystal. But to your questions of what happens when you have a few embryos that rotate in a different direction, that definitely happens, and what we see, if you have enough of them, these systems become no longer chiral, and you lose this odd elasticity behavior. So basically, yeah.
Cool, thank you.
I have the similar question as Patrick. I don't know if you're familiar with linear and particle linear. It's a simulated system that each particle have attraction power and the attraction power when they are having certain distance. So yeah, so I saw some experiments show that if you put different kind of particle linear or called linear particle together, they will form a cell. I mean, emergent scale cell. So I don't know if you observe similar thing, like you saw these crystals having a behavior like a single cell.
So I'm not familiar with the simulation platform, but what kind of cell do they form? As in, what kind of properties do they have?
I mean, it's like the collection of these cells, collection of these particles behave like a single cell. They move, they translate in this space.
Right. So the translation part is sort of what I show you in this video towards the end, that we do sometimes see that when you get these clusters, sometimes they rotate, sometimes they translate, and sometimes they rotate and translate. And that's something that we are still looking into, and I suspect is probably quite geometry dependent. That, you know, depending on the history of how the cluster is being assembled, then you might get different of geometry, and that actually dictates a lot what happens next to that cluster. But we haven't looked too much into it yet.
Okay, thank you.
Two quick things. One is, have you ever looked at any of the, let's say, robustness properties? Like if you've got, you know, the phenomena that you showed today, you try to interfere with it, right? Manually, you go in and you sort of do anything. To what extent is it able to come back from those kind of perturbations back into the shape that it had? Anything like that?
Yeah, so it depends on what kind of perturbation that you do. So what we have done was that if you completely disassemble it, so you know you stir the well completely so that these embryos fall apart, then actually very quickly they will spontaneously reform again. Meaning to say, because the embryos will again swim to the surface, it's almost like you're resetting the system, and then they start making new crystals. If it is a more gentle kind of perturbation, like for example, if I take a pipette tip and sort of draw a line and break the crystal apart, then actually they do have quite, they are able to heal quite well, meaning to say very quickly they come back together and then sort of reorganize a little bit, but then reform the crystal. So I would say they are, in that sense, you know, they are quite robust. And on top of that, I think they are more robust than, say, crystals. You know, if you have passive crystals and you break them apart and you try to stitch them together, typically you will have dislocation lines near the boundary. But then because these embryos are rotating, I think it gives them an additional degrees of freedom to fall back into their low energy barrier. So I think they heal better in that sense.
Cool. Okay. And another thing, if you sort of take a step back and think about, in the system, you have some initial properties that each of the elements have, and then there's this collective behavior that you've shown us today. What do you think is the evolvability of this system? If you were going to either try to design for specific system level outcomes, or you try to evolve, so basically some kind of evolutionary search for some specific large scale properties, how rough do you think that space is? Do you think that would be an easy transition to make, right? So design the low level properties to get a particular system level outcome, or do you think it's a super rugged space that's going to be hard to engineer through?
Right. So I would have to think about how rugged this landscape would look like. But then, you know, in terms of the parameters that you can tune to get different system level outcome, I would say there's a lot of parameters that you can tune. So for example, the morphology, the hydrodynamics are essentially it's almost like, you know, if you can change the morphology, then you change the interaction strengths with it. And if you can imagine, you know, designing more complex shapes, then you can also, you know, sort of program in what kind of cluster geometry that you would like, for example. And this is sort of what we wanted, or the hope is that what we wanted to do with this platinum, because then we have different, we are able to poke each embryo at a time to see how that affect things. And the other thing is that, you know, then we can mix different species together, which has different morphology and hydrodynamic flow field, to see how different things would do. But at this point, it's hard for me to predict how rugged it's going to be. Yeah.
Gotcha. Okay. Okay. Well, thank you so much. Yeah, that was really cool. Thank you.
Thank you.
Yeah. Right. Thanks. Right. See you, everybody.
Thanks, everybody.